Good afternoon, everyone. Thanks for staying at the summit to listen to me talk. Before I start, I did want to say something probably as an aside. Today is at NASA, we are celebrating the Day of Remembrance. So every year, and we take the whole week at NASA to think about the previous journeys and experiences we've had at NASA and the lessons we can learn in terms of safety and a safety culture. So we remember Columbia, Challenger, and Apollo 1. So we actually take this week to have our employees kind of listen to our leadership, reinstill the culture of safety, but also innovation at the agency. So today's a special day. We've had, this week, we've got different ceremonies at Arlington National Cemetery and with our workforce. So this is a week where sometimes at NASA we reflect on the past. Now, today we're actually looking at the future. And so as I was telling someone earlier, this is a good bookend for you all. I think for those of you that stayed today, at the beginning of the day, we look back in terms of the James Webb Space Telescope, the incredible achievement, how we achieved that, the data that came out of that. Now, as we look forward, how do we drive that innovation within the agency and within the nation? So first, I'll start off a little bit about me. I'm not going to PowerPoint slide you to death here today. I'm the Agency Chief Technologist, or ACT as I call it, at NASA headquarters. We support our senior NASA leadership, Bill Nelson, Pam Maroy, and Jim Free, in terms of technology strategy, policy, and economics, in terms of our particular office at the agency at NASA headquarters. I'm in the Office of Office of Technology, Policy, and Strategy within the A-Suite, and basically look at several moves ahead in terms of the agency, in terms of technology disruption, places we can infuse technologies, and how we're investing within the agency. And I've been at NASA about a year, first year as a civil servant, coming from commercial industry, 23 years in space and aviation. So prior to joining NASA, I was actually at an aviation autonomy startup called Reliable Robotics, where we were trying to automate the world's cargo airplanes to fly themselves. It's a very interesting problem there, dealing with human-machine interfaces. Prior to that, working for Jeff Bezos at Blue Origin in terms of maturing the lunar lander program at Blue. In that sense, trying to have large cargo landers and crewed landers that use machine learning and other algorithms to land humans on the moon. So prior to that, worked for Richard Branson for 5 years at Virgin Galactic. And that's particular instance, looking at the Launcher One program, basically looking at an autonomous rocket in the left wing of a 747 and launching small satellites to space. So, and prior to that, 12 years at a company in Atlanta called SpaceWorks, doing a lot of advanced concepts, systems analysis, starting new companies. And actually part of that started at Georgia Tech in Atlanta, Georgia. And actually Dr. Bilchin right there, who wrote a new book, I believe, on AI, that I think you'll find here. Actually, he and I went to school together. So it's good to see Dr. Bilchin here at Booz Allen. So kind of feel a little bit at home with Pat here. So at NASA, as Agency Chief Technologist, my portfolio is to look at our technology strategy, look at where we can leverage the disruption that's happening. So things coming into the agency, actually two major technology areas I've been focused on beyond some of the others that you might traditionally think of in terms of technology. Those include quantum sensing and AI. Those have actually, over the last year, our office in particular has been supporting the agency, thinking about those technologies more strategically. As a chief technologist, though, I'm not kind of responsible for cybersecurity or IT. We do have a chief information officer, chief data officer at NASA, and I work very closely with those entities and personnel and staff and leaders on those kinds of collaborative areas. So for instance, an area where we collaborate together is in AI. We look at AI obviously for our IT functions and other things, but also AI for engineering, digital engineering, machine learning, and how we use it. And that also brings together our chief scientists. So actually, our chief scientists at NASA, our CIO, myself, and others, we many times collaborate together of how we as an agency can leverage these tools and technologies. All right, so let's see if this works. And next slide. All right. So Um, Once again, I'm not going to PowerPoint you to death. Yeah, for me, as I was thinking about this, how are we using AI? And really, at the end of the day, for us, it's our strategic objectives. And ultimately, if you look at the NASA vision, it is to help humanity and benefit humanity. Now, we decompose that objective into looking at science, national posture, and inspiration. Both that is the knowledge of we as humans have, how do we help US industry, academia, and how do we inspire? Those three pillars of science, national posture, and inspiration kind of drive a lot of our thinking of what we're doing. And there's decomposition of those objectives and stakeholders that play into that. So, for instance, in science, we have a National Academy's decadal survey process where we canvass our scientific community for the top scientific objectives we should attempt in planetary science and heliophysics and earth science. And so there are processes that drive those scientific objectives, and those then get promulgated into actual missions, or science missions, space science missions, planetary missions, human space exploration. We also mature technology. So different parts of the agency are working on research development internally with NASA civil servants, as well as with industry and academia. Now, in all those three areas, we've been using AI, machine learning for years. So in terms of generative AI, yes, last year, I think we were all there when ChatGPT came on board. I was at Reliable Robotics, and it was an awesome time to be in the room when the coding team realized this was available to them. It was like a eureka moment. To still recall that moment very, very crisply last year when I was in industry. But separate from that, we've been using AI and machine learning for many years at NASA, from earth science data to how we're looking at different data sets and missions. So for us, it's not a new thing, specifically our science portion of NASA, but now we're looking at digital engineering, digital twins, as was mentioned in the previous panel. We've been looking at that for many years, and how do we use that in missions? And now how do we use these large language models, obviously, but also how do we couple AI with things like 3D manufacturing? So different examples of how we're using AI or been thinking about using AI as we go forward are in these actual missions. So as we look in autonomous missions on other planets, on the lunar surface, or on Mars, we've got a helicopter on Mars. That's the Ingenuity helicopter you see. That's flown more than 60 missions. How do we, in future generations of Mars helicopters that we're looking at, instill more autonomous operations to decouple such helicopters from, let's say, the rovers that they are leveraging in terms of like a base station. So those kinds of missions we're looking at. We've got missions on the lunar surface looking at autonomy. We've got a program at JPL called Cadre that's looking at a collaborative set of rovers that use autonomy. And also, as we look out further in terms of decreasing the life cycle costs of these missions, how can autonomy AI support those kinds of missions and operations? We also look at science, obviously, and a lot of that science is looking at as observational data in many different wavelengths from Earth to the planets of our solar system. This particular picture is of a project we did with NASA Goddard and academia that looked at using a human-trained data set to then identify and characterize how many trees are in Western Africa. So a human-trained data set was used on tens of thousands to identify tens of thousands of trees. Then that data set was used to identify more than 1 billion trees and just the population of those trees in potentially arid areas. Now, that data can now be used to help determine the carbon footprint of all those trees in Western Africa. And we are using those kinds of AI machine learning techniques all across the board. The other thing we think about, both in terms of myself, the CIO, and other parts of their agencies, as we go forward in time, how do we work more digitally with all these tools? So machine learning, digital twins, model-based systems engineering, AI, all those tools, coupled with kind of physical tools like we have with 3D manufacturing, to actually work faster. For me, the 21st century in aerospace and in the agency is also how do we execute rapidly, bring decision-making down to lower levels, and can execute rapidly on these missions with the constrained budgets that we have. And working digitally, I think, will allow us to operate faster, reduce overall lifecycle cost, and hopefully develop safer systems. So this actual picture, I think, is representative of projects we've got ongoing at NASA Goddard, where researchers are coupling AI, machine learning with actually 3D printing to then 3D print structures that humans would never have imagined that would be more rigid or weigh less. And so, thus, the AI machine learning capabilities are developing things that will make these systems lighter and cheaper that we would never have imagined as humans to create. So, I think a lot of tools and techniques that I think beyond just large language models and generative AI that we can provide to our civil servant workforce and to the industry, and to then promulgate that out to the contractors that are supporting us at NASA. Let's see, next slide. And then here I've got different examples I'll probably go through of different uses of AI and ML. Some of these are, I would say, examples that we're using. Some of these we've actually used in actual missions. So these kinds of examples range from kind of the observational side. So starting from the right-hand side, we've been using, this particular example is kind of cool, and Dr. Bilton would like this. This is actually a collaborative project between NASA Langley Commercial Industry and Georgia Tech, where we actually took some data from Calypso LiDAR. Calypso is one of our spacecraft that you see there. We took some of the data that was coming from Calypso and work with academia and researchers to look at how could we identify the health of coral reefs. So for instance, a lot of researchers are looking at which coral reefs on the planet are at most risk. And so in this particular case, we were using Calypso data, not particularly developed to help in this problem, with trained data sets to identify, okay, which of the coral reefs that the Calypso data is observing are at most risk. And so that was kind of a cool experiment we did. I think the results of this were published, of this particular study were published in 2021 during COVID. But it was kind of a cool test case study of using Earth observational data in partnership with academia to look at a problem the original instruments were never designed or optimized to solve. So, which was kind of cool. There's multiple other examples of using Earth observation data in this way in terms of AI and ML. Another example I kind of like is the middle example. So, okay, landing on Mars is pretty difficult, and a lot of nations have tried. The last few times we've been pretty successful, and I think we're celebrating 20 plus years since the Mars Pathfinder landing, so kind of a cool anniversary. But it's pretty hard to land on Mars, even harder to land in terms of a particular place you want to land in. So if you're trying to land in a place and return samples back to Earth, you want to land in a place where you think you'll have pretty good samples that might have evidence of possibly life on the surface of Mars, or historical life in that sense. So you need high landing accuracy. Well, one of the ways you can do that is actually a way we've been using, and we've used on the Perseverance rover to land it on the surface of Mars to reduce what we call the landing ellipse. So a landing ellipse is the uncertainty of where you might land on the Martian surface or the lunar surface. And technologies where a camera system on this vehicle that's entering the Mars atmosphere and coming down is comparing the pictures it's seeing with the data sets we've gathered from previous Mars orbiters. And doing that comparison, it can then tell itself where it is. There's no GPS on Mars, so you got to figure out where you are. And so using these terrain relative navigation technologies for identification of landmarks, to seeing where you are, maneuvering yourself to land and reduce the landing ellipse error that you have on the Martian surface. So we're using similar techniques, or thinking about using similar techniques like TRN on the lunar surface. We are funding several, we are the anchor tenants, anchor customers of several small lunar landers that are moving, going to land on the lunar surface, and they're using some of these technologies as well. Another reason why I'm kind of excited about that one is when I was at Blue Origin, we actually tested some of those technologies on New Shepard, which is the vertical takeoff, vertical landing suborbital vehicle at Blue Origin. So once again, we've done terrestrial tests with Blue Origin, Maston on these technologies, and I've actually flown these technologies on Mars and looking to apply these technologies, so comparing orbital data sets with the real-time images these landers are seeing to help them land more accurately. So kind of cool there. Another one is a periodic table of life project called PEDAL. And this is kind of an open source framework that was developed a few years ago to look at how to use AI to help examine linkages in large language models relative to biological data. So once again, a lot of stuff people are looking at, but this was actually even a few years ago. So before ChatGPT, we were actually developing these kinds of frameworks to look at how to help using biological models understand some of these large language models. So kind of a cool experiment there. Once again, the idea of using AI ML for Earth is a great application, but we also explore the rest of the solar system. So in this case, we're also looking at how we can use AI ML to look at other planetary bodies. What excites me about this century is the achievements that NASA could possibly help in. And some of those achievements include our human exploration goals of going to the moon and landing humans on Mars, but it also extends to future observatories. So we talked about James Webb. I also hope that in this century, we can also image an exoplanet. And so we have a Habitable Worlds Observer program whose objective is that, basically to return a picture to humanity of a planet in another solar system. But in addition, there are other very cool missions regarding life that could be here in our solar system. So Europa and Enceladus, the moons of Jupiter and Saturn, are icy worlds where we think there might be hydrothermal vents underneath ice layers that could be areas of possible life. So in this particular case, can we use images of Europa, one of the moons in our solar system, to detect different ice plates and use AI and ML to help detect those ice plates? So kind of cool application. We've also got missions going to Titan, and we are interested in the composition of Titan. And so using AI ML to take observational imagery from Titan to observe methane cloud detections or formations. Another example of how we're using possibly AI ML to help in the search for life is JPL has looked at how to use AI and ML to help develop autonomous underwater robots to be used on Europa. So once again, we're using AI ML to help us identify ice plates in Europa. We're also using AI ML in missions that we're formulating maybe 2 or 3 decades from now to look at autonomous systems that would then go through the ice, melt, and go explore these ocean worlds, these icy ocean worlds. What's actually kind of cool about that one is when I was a freshman at Georgia Tech with Dr. Bilchin, that was one of my first undergraduate design projects, which was to look at a Europa lander mission. So it's kind of cool. We never, I think, imagined 25 years ago, we'd be using AI ML to help us develop the missions, analyze the orbital imagery, and then also use that to help these robotic underwater submarines navigate these ocean worlds. So kind of a cool set of examples of how we're using AI ML across the agency. If you want to know more, there's obviously, you can do a lot of searching. All federal government agencies, or many of them, also put out an AI inventory. So if you actually search NASA AI inventory, you can get a list of some of these projects that we're working on relative to AI ML, and that's an annual inventory we update. Other federal agencies update that as well. Another resource for you all to understand AI ML autonomy technologies we're developing at NASA is a website we call techport.nasa.gov, where we list many of the technologies we're investing in. So if you're kind of wondering, what are you investing in at NASA? Well, techport.nasa.gov is a good website for you all to go to understand not just AI ML, but a whole range of technologies. And the other thing I think we all, relative to this summit and the government we're wrestling with, is AI ML and our strategic understanding, strategic use of that. And so, for instance, I think earlier today, there were conversations about the executive order and an OMB letter relative to all federal government agencies. And so I think if I came back here a year from now, all those White House stakeholder interests for AI and ML will result in a chief AI officer at many of these agencies. So actually, I would encourage you next year probably to have a chief AI officer across the federal government panel, because I think we will have named many of these agencies those individuals and define those roles and responsibilities, which is kind of cool to think about. So Not saying what panels you should have next year, but that might be a good one to have because we'll have those named individuals. It's a pretty exciting time at NASA relative to the challenges we have of human exploration, science, urban air mobility, which we also work on and leverage some of these autonomy technologies and AI technologies, and going back to the moon. For me, and I was speaking to Pat earlier, it was really strange to think that, 25 years ago, we were at Georgia Tech, and who knew that, I'd be at NASA when we're headed back to the moon, and, Pat's writing a book on AI, couldn't have imagined stuff like that, right? But for me, it's all about kind of not just the inspiration, science, but the strategic objectives of these kinds of endeavors. And what I'll leave you with is all of these technologies are helping humanity. And particularly for me, I look at the lunar surface and lunar exploration, which is pretty important at NASA and to our stakeholders, and leave you with the final thing of what AI, ML, and all these sorts of technologies can get us to, which is what I would call the lunar moment. As we look at investing in these technologies and lunar exploration, for me, it's also about the moment that humans walk on the lunar surface. And from that moment forward, there will always be a human on the lunar surface, right? And these kinds of technologies will enable us to enable those humans to more permanently, for longer term, and sustainably live in these planetary bodies and live in space. I think it's a pretty powerful tool that I think 25 years ago we would never have imagined would be in our tool set. And I think the machines we design, the data we look at, the experiments we do, and the knowledge we gain will be enabled by all these tools, and we're a part of it. So thank you very much. All right. Maybe one or two? Yeah. So. Oh, Pat. Yes. Dr. Belchin, please. Go ahead.
So I do have a question. So, you were doing commercial space like before it was cool. Before it was cool. I've really been working that for a huge chunk of your career, a lot of startups, innovative concepts, high risk things. Now, I have read that sometimes when people with that background go into the government, there are cultural challenges because the government has structured processes, ways of doing things. So when you were appointed chief technologist, I thought this is really exciting, both for you and for NASA. But can you give us, I'm just really curious on your perspective of how you bring that commercial perspective into NASA, and then either challenges or approaches to try and help a federal agency adopt a commercial mindset.
Yes. I think, once again, I'm not coming into NASA as a novice. I've dealt with NASA for 23 years, 25 years. And NASA, part of NASA actually paid for grad school when I was at Georgia Tech. NASA funded our research lab. And so I'm kind of a product of the space agency in some sense. So I think I have submitted contracts ranging from $50,000 to $6 billion to the government. I proposed that. I've been involved in lobbying stakeholders. I've been involved in putting technical teams together and understand that ecosystem of working programs with stakeholders, with the government, with NASA. And so, and going to NASA headquarters in my career and other centers. So I was pretty familiar with the ecosystem and how NASA operates. So that didn't really surprise me. So I knew what I was getting into. So first of all, because people warned me or it's like, oh, are you sure about this? So I think having that experience is helpful. I also probably, an approach I use is probably kind of a Platonic kind of approach of questioning. So once again, in these meetings, you kind of, in order to get people to maybe reach a conclusion, you ask, well, from fundamental principles or first principles, why this, why this, why this? And so I think I can also point to successes. So the COTS program with commercial cargo to the International Space Station, commercial crew resupply to the International Space Station, these other models that have worked successfully, those successes help us advocate for additional public-private partnerships. When I was in industry, we helped create public-private partnerships from, I wouldn't say from scratch, but in collaboration with the government. And so those successful partnerships we can now point to continue the momentum of these partnerships. So one of the reasons I came into the government was to continue this momentum of partnerships and say, hey, these have been successful. Let's start expanding them. And so now what you see, the Human Landing System program, which is a public-private partnership of SpaceX and Blue Origin developing propellant depot-based single-stage lunar landers for humans. Those are not architectures that NASA probably would have come out with on its own, but in collaboration with industry and their co-funding, we can now work with them to mature those technologies, support them where we can. And so I think those smaller successes over the last 2 decades and continuing those successes in low Earth orbit and beyond, using first principles, I think, and also I think finally for me, the icing on the cake of why to take this job in the government is also leadership. So I don't know if many of you know our Deputy NASA Administrator, Pam Melroy. I knew Pam when she was at DARPA, and that was probably the icing on the cake for me to take this job. There's a spirit of public-private partnership at NASA. I know that because I was part of that in industry. We have great partnerships with companies that didn't exist 20 years ago that are pretty substantial and have great capabilities. And then finally, the internal leadership, like Pam Melroy, is supportive of these kinds of collaborations. I think those kinds of things gave me energy, confidence to come into this job, that people have an openness, and leadership itself has an openness to these kinds of collaborations. We've got to be measured. Also, for me, it's trying to talk about how this world we are in happened, and relating internally. What I realize is sometimes I tell people at NASA stories of how we got here, because sometimes even that history is not written, of how this innovation happened with industry or this public-private partnership. So I don't know, that's probably a long-winded answer to your question, but yeah. All right. Probably one more. Yeah. One more.
Did you want to ask?
All right. Okay. All right. Well, that's it. Well, thank you very much.